start a fresh one. So we're going to talk about unit tangent vectors and then curvature. Then we'll get into some application questions. So unit tangent vector, you have a relatively simple concept. The unit tangent vector is the derivative of a vector valued function divided by the magnitude of that vector valued function's derivative. So so not too bad conceptually, just carrying out the process. You're going to see a lot of similarity to what we just did in terms of the derivative part and simplifying, but the application is incredibly different, right? So r prime of t (6t plus 2) negative 12t squared, and then 6. All right. So just the derivative of each component. That's all. Now I need to find the magnitude. So I'm going to just kind of strip this down a little bit. Square each part, add them together, you know the drill. Right. More often than not, these problems will clean up kind of nicely just based off of the ones that I select for us to do. But sometimes they just don't. This is a case where it just doesn't. Right. And you'll find that that tends to happen with more of the polynomial. As I was mentioning that before, you start looking forward to the trig and conic sections, because polynomials and other ordinary functions like linear functions, you know, your quadratics, cubics, and all that stuff, they lend themselves to the ordinary XY coordinate system. So there aren't too many instances where you would want to convert over into vector valued form in order to evaluate these functions. I mean, when you're in 3 dimensions, you don't have a choice. But when you do have a choice, you tend to want to stick with, you know, what is familiar and what works. So this is just one of those instances where it just gets kind of ugly, but we got to clean it up and then put it all together. But in the final analysis, it won't be that bad. You know, it's just writing. So 36t squared, we're going to have a couple of 12t's, so 24t plus 4 plus yo.
Can we just cancel those squares since it was like a radical?
Well, the plus signs messed that up.
Oh, okay.
Yeah, if those plus signs weren't there, you could, but unfortunately. All right, so we're just going to combine some terms. Looks like you got 144 t to the 4th. I'm going to have 36t squared. Looks like a 24t and a 40. All under a radical. All right, now they're all even, they're all divisible by 4, so we could clean it up a smidge. We could try factoring by grouping. We can try a bunch of different things. I wouldn't try too much though, because without context, it's not really worth getting into. But you know, if you see something right away, then you could go for it. But even if, let's say, for example, if I did factoring by grouping here, I could try to factor out a 36t squared, and that would give me 4t squared plus 1. But then on the other end, and 4t squared plus 1 itself doesn't factor. But then for the other half, I'd only be able to pull out, looks like a 4. Oh no, I can pull out an 8, which would give me 3t plus 5. It's not going to have, we're not going to have common factors. It's just going to be a dead end. So I wouldn't even bother. All right. So the next step is to divide each component of r prime of t by the magnitude of r prime of t. And that'll give us t of t. All right, capital T of lowercase t. The capital T is referencing the unit tangent. The lowercase t is that it's in terms of t. All right, so I'm going to rewrite this. And I'm going to take this jimmy jammy here, copy it, shrink it down to like damn near nothing. And make it the denominator of each piece. Let me just bring it down here for a sec. Move this over. It's like Calc 3, the course where we teach you to hate polynomials. And so you think back to Calc 1, it's like, oh, the power rule for power functions. That's great. It's so easy. And then it's like, why do we have to deal with this trig? The power rule is so much easier. Why can't we just deal with that? Now it's like, oh, forget the power rule. Just give me some trig. Give me some derivative of sine is equal to cosine, you know, that kind of thing. That was a poor quality comma. I'm getting a fresh one in there. Yeah, that one's not much better. That's really it, right? That's conceptually, there's really nothing to it. It's just, you got to write a lot. Sucks. Not fun. Not fun like the problems on the last page. The last page, that was interesting. You know, it's like you're starting to think about, okay, what could be some of the applications of that? Here, we're just kind of scratching the surface on the unit tangent vector, so we don't know what the applications will be yet. But we will. We'll make it fun. We're getting there. So, r prime of t negative a, right, again, I'm doing it in component form, sine t, a cosine t, all right, the magnitude of which, well, we've kind of beaten this one to death. I'll just check for a pulse real quick. Just doing it one more time. So we're looking at a squared sine squared plus a squared cosine squared get enough experience with these, you start recognizing the inherent patterns that exist. You got the common a squared, and you factor that out, sine squared plus cosine squared. Still under the radical. This is one of those situations, though, where if you gave it a moment's thought before you started the problem, you'd realize you really don't need to do any of this work, because if I go to find the unit tangent vector, and I know that that's taking the derivative vector and dividing it by, in each case, whatever the magnitude is, and we know that this is the equation of a circle in parametric form initially, the vector value function, then really it would just be a matter of taking off whatever the coefficient is from my derivative vector in order to get the unit tangent vector. Because really, if you think about it, the main ingredient, the rationale behind a unit tangent, forget about unit tangent vector, but a unit tangent is that its magnitude has to be equal to 1. If I square each component here, negative sine squared and cosine squared, I'll get sine squared plus cosine squared equals 1. So if your two components in your derivative involve sine and cosine and are only a coefficient away from being that, then just strip away the coefficients, leave the signs, SIGN sign, leave those signs, and you'll have your unit tangent vector. It wasn't a lengthy problem to begin with, but even still, you kind of want to trim the fat a little bit. Right? So this one should look pretty familiar because they're all, like, in a sense, repeats of the problems on the previous page. That was alliterative. It's asking for the unit tangent vector for this parabola. All right, so you can steal your work because we did it already. Oh wait, no, we didn't. We were close. It was similar. And t squared, not t squared plus 1. Dang it. Still essentially the same idea, but this is kind of a repeat of number 8, so I don't have a problem skipping this one, just for the sake of sanity. So let's hop on over to curvature, which is page 49. Let's stop this.